In a lab in Hungary, protons struck lithium and the sparks flew apart at an angle that physics forbids. The suspect is a force hiding between matter and light. Tonight we hunt it. A particle that wears the photon's face, a laser fired at a solid wall, a clue that dissolved. If this is the kind of question you love sitting with, a quick like or subscribe really helps the channel grow. Prepare yourselves. We begin. Tonight we start with a question so simple that most people never think to ask it. When two magnets snap together, what actually crosses the gap between them? There is empty space in that gap. Air, maybe. Nothing you can hold. And yet something reaches across it and pulls. Physics has a strange and beautiful answer to this, and the answer is the key to everything we are hunting tonight. Something crosses. A particle. Every force in nature works this way. A force is a conversation, and every conversation needs a messenger. Two objects want to push or pull on each other, so they throw something back and forth between them. The thing they throw is the messenger of that force. For electricity and magnetism, the messenger is the photon, a particle of light. When your magnets snap together, they are trading photons you cannot see. When you touch a table and your hand stops, photons are passing between the electrons in your skin and the electrons in the wood, and they are saying, in the only language they have, stay back. The strong force has its own messengers. Physicists call them gluons, and they grip quarks inside every proton in your body with a violence that keeps them locked away forever. The weak force has messengers too, called the W and the Z, and they are heavy, so heavy that their reach dies before it crosses even a fraction of a single atomic nucleus. Gravity, we suspect, has one as well, though nobody has ever caught it. 4 forces, 4 sets of messengers. That is the entire list of ways that anything in the universe touches anything else, and that list is almost certainly incomplete. Physicists have spent 40 years looking for a 5th force, and the reason is straightforward. The 4 we know cannot explain what we see when we look at the sky. Galaxies spin too fast for the matter inside them. Clusters hold together with far more gravity than their stars can supply. Something enormous is out there, 5 times heavier than everything we can see, and it ignores all 4 of our messengers completely. So there is probably a 5th conversation happening, and here is the constraint that shapes the entire hunt. If a 5th force exists, it must have a messenger. That messenger has to be findable. It has to be able to be made somewhere, somehow, by smashing things hard enough. Because that is what a messenger is. It is a ripple in a field, and if you hit a field hard enough, it ripples. For decades, the search assumed the 5th messenger would be heavy, enormously heavy, something you would need a machine the size of a city to produce. Billions of dollars went into that assumption. The Large Hadron Collider under the Alps was built partly on it. 20 years of searching at the highest energies humans can reach has turned up an empty room. Which forces a very uncomfortable question. What if the 5th messenger is light? What if it is small and feeble, and it has been drifting through every experiment we ever built, passing straight through the detectors like a ghost through a wall, because it barely speaks to us at all? A messenger that's shy would need a door. Some crack in our world it could slip through. There is exactly one obvious crack, and it is the messenger we already have. Imagine you are a particle from a hidden world, and you want to touch ours. You have a problem. Our world is built out of a handful of charges, and if you carry none of them, you are a ghost. You pass through the Earth, you pass through the Sun, you pass through every detector ever built, and nobody ever knows you are there. So you need a way in, and the way in has to be through something that already touches everything. That thing is the photon. Look at what the photon actually does. It holds every electron in orbit around every nucleus in your body. It carries the heat of the sun across 93 million miles of vacuum, the distance you would cover driving non-stop for 170 years. It is why chemistry works. It is why your eyes work. Almost everything that happens in ordinary matter, from a match lighting to a nerve firing to a rock staying solid, is the photon doing its job. The photon is the universal translator. Matter speaks, and light carries the words. So if you were a hidden force looking for a way to reach into our reality, you would go through the translator. You would not build your own bridge to every particle we have. You would tap the one bridge that already runs everywhere. The way you do that is by looking like light. This is the idea at the center of tonight's entire hunt. A new particle that shares a family resemblance with the photon. Same kind of thing, same shape, same job description, with one difference that changes everything. It has mass. The photon has none. That is why light travels forever, why a star 10 billion light-years away can still reach a telescope on Earth. A massless messenger has infinite reach. A messenger with mass has a leash. The heavier it is, the shorter the leash. Give the photon a mass, even a tiny one, and it becomes something else entirely. A force that fades out after a certain distance. A force that could be operating right now inside every atom in your body and switching off before it ever gets far enough for anyone to notice. Physicists gave this hypothetical twin a name, the dark photon. The name is a little unfair because it would carry a hidden kind of light, invisible to our eyes the way radio waves are invisible, present the whole time and simply outside our range, and the beautiful part is that you get this idea almost for free. You do not have to invent strange new mathematics to make it work. The rules that give us the photon in the first place are a particular kind of symmetry, and that symmetry is the simplest one physics has. Writing down a second copy of it takes one line, a second photon, belonging to a world that is not ours, which raises the obvious objection, and it is a good one. If this twin lives in another sector, and our matter carries no hidden charge, then the two worlds should slide past each other forever, untouching, sealed. In 1986, a physicist working quietly on the problem realized that the seal leaks, and the leak is not a flaw in the theory, it is a prediction of it. The idea arrived in a paper barely a few pages long, and it took the physics world almost 20 years to notice what it meant. The man who wrote it was Bob Holdom, and the year was 1986. He was thinking about two worlds sealed off from each other, and he found the hole in the wall. Here is the picture, and it is easier than you expect. Think of two guitar strings lying side by side. Pluck one. It vibrates. The other one sits still because nothing connects them. Now lay a thin sheet of wood across both strings. Pluck the first string again. This time the second one hums. It has picked up a whisper of the first one's motion through the thing they share. Holdom's insight was that the universe has a sheet of wood lying across the strings, and it is made of the particles nobody has found yet. Suppose that somewhere out there, at some enormous mass, at energies far beyond anything we can build, there exists even one particle that carries both charges, our electric charge and their hidden charge. One single particle, heavy enough that we have never made one, sitting quietly in the mathematics. That particle listens to both photons, ours and theirs. And in quantum mechanics, a particle does not have to exist to matter. It can flicker into being for an instant, borrowing energy from nothing, and vanish before the universe notices. Physicists call these virtual particles, and they are the reason the vacuum of empty space is a boiling, restless thing rather than an emptiness. So our photon travels along. For a fraction of an instant, it flickers into a pair of these heavy hybrid particles. They exist for less time than it takes light to cross a proton, and when they collapse back down, they can collapse into the wrong photon. Ours goes in, theirs comes out. The two fields have been quietly stirred together, and the stirring is permanent. Physicists call it kinetic mixing, and the consequence is genuinely dizzying. Every photon in existence is very slightly the other thing. The light coming off your ceiling right now, the light that left the sun 8 minutes ago, the light from the first star still crossing the void after 13 billion years. Every one of those photons carries a faint contamination of a field that belongs to a world we have never seen, and it has been that way since the universe was a fraction of a second old. Turn it around and the picture gets stranger. It means a dark photon, born in the hidden sector with no business here at all, would carry a whisper of our electric charge. It could feel an electron. It could be made by a proton. It could be produced right now in any laboratory on Earth where particles are being smashed together, and it would come out looking almost exactly like a photon, except heavier, and it would leave without saying a word. You do not need to add this leak by hand. If both worlds exist, the leak is nearly unavoidable. The mathematics generates it whether you want it or not. which turns the whole question into a number. How big is the leak? And that number, it turns out, is the most important number nobody has ever measured. Let us be honest about how strange the next idea sounds, because it deserves to be said plainly before it is defended. The proposal is that there is a second physics, a whole one, not a single lonely particle drifting somewhere, an entire sector with its own charges, its own forces, its own light, its own rules, sharing this same space, passing through this room, through the earth, through the sun, and through everything you've ever touched. The first reaction to this is that it sounds like fantasy. The second reaction, once you look at the accounting, is that something like it is almost demanded. Here is the accounting. Add up everything we can see. Every star in every galaxy, every planet, every rock, every cloud of gas glowing between the stars, every black hole, every neutrino streaming out of every stellar core, everything that emits light, absorbs light, or blocks it. That is roughly 1/6 of the matter in the universe. The other 5/6 is something else. We know it is there because it bends light around galaxy clusters. We know it is there because galaxies spin like a record player instead of like a solar system, with their outer stars whipping around far faster than the visible mass could ever hold. We know its shape. We know its total. We have mapped where it clumps across billions of light years. We have never seen a single particle of it. For 30 years, the leading guess was a heavy particle that spoke to us through the weak force. Faintly, rarely, but occasionally. Physicists built enormous tanks of liquid xenon and buried them a mile underground to hide from cosmic rays. They waited for one atom to twitch. Those detectors got better by a factor of 1,000,000. Not one convincing twitch. So the field started asking a different question. What if the missing 5/6 does not use any of our four forces at all? What if it is dark in the deepest possible sense, meaning it is deaf to every messenger we possess? Then it would need messengers of its own. It would need a force to bind itself, a force to sculpt the halos it forms around galaxies, a way to have a history. And a sector with its own force can be as rich as ours. It could have its own version of the electron, its own version of atoms, its own chemistry in principle, running quietly in the same room you are sitting in, entirely blind to everything you are made of. The one thing that would connect the two worlds is the leak we just described, a tiny, unavoidable contamination between our photon and theirs. That leak is called a portal, and it is why this hunt is not idle speculation. It is the only door we have. If the dark sector exists and the portal is closed, we will never learn anything about the other 5/6 of reality, ever, for as long as our species lasts. If the portal is even slightly open, we can walk through it. So the entire question narrows down to one number, the size of the crack under the door, and there is a reason to believe that number sits in a very particular place, a place we can almost reach. Physicists call it epsilon, and it is the smallest important number in modern physics. Epsilon measures the leak. How much of the dark photon bleeds into ours? Set it to 1, and the two worlds are the same world, and everything falls apart immediately because we would have noticed. Set it to 0, and the wall is perfect. The hidden sector is sealed forever, and nothing we ever build will find it. The truth is somewhere in between, and the range is almost comically wide. The searches tonight will cover values from about 1 part in 1,000 down to 1 part in a quadrillion. To feel that spread, picture a wall between two rooms. At the top of the range, the crack under the door is wide enough to slide a coin through. At the bottom, you are looking for a gap narrower than a single atom, in a wall the size of a continent, and you have to prove it is there without ever going into the other room. That is the search space. It spans 12 powers of 10. Every experiment tonight is a flashlight pointed at a different patch of it. And in the middle of that enormous range, theory does something helpful. It points. Remember where the leak comes from. Heavy particles, flickering in and out of the vacuum, carrying both charges at once. When you actually calculate the size of that effect, the mathematics spits out a number. It depends on how many hybrid particles exist and how heavy they are, so it is a guess rather than a prediction. But the natural size lands somewhere around 1 part in 1,000 to 1 part in 10,000, sitting right there at the near edge of what our machines can reach. and a second signpost points to the same neighbourhood, coming from a completely different direction. It comes from cosmology. In the first moments after the Big Bang, everything was in contact with everything. If the dark sector was talking to us at all through the portal, it was in that furnace. As the universe expanded and cooled, that conversation would have shut off, and whatever amount of dark matter existed at the moment the conversation stopped is the amount that is still here now, frozen in. That is the beautiful part. Run the calculation backwards from the amount of dark matter we actually measure in the sky today, and it tells you how strong the portal had to be. The answer lands in the same band, somewhere near 1 part in 10,000, for dark matter in the range of masses we can produce in a laboratory. Two completely unrelated arguments, one from quantum mechanics and one from the expansion of the cosmos, pointing at the same crack in the same door. This is why hundreds of physicists have spent their careers here. There is a target, a finite region of the map marked and shaded, and it is reachable with machines that already exist. Experiments have been walking into that shaded region for a decade now, one narrow strip at a time, finding nothing and crossing it off. And then, in a small building in a small city in eastern Hungary, an experiment that was never even looking for this saw something come out of a lithium target at an angle that made no sense at all. The machine was old, the building was ordinary, the city was Debrecen, in the east of Hungary, and the laboratory had a reputation for careful, unglamorous nuclear work rather than headlines. In 2015, a team there under a physicist named Attila Krasnohorkai was doing an experiment that sounds almost quaint compared to the Large Hadron Collider. They took a beam of protons, they aimed it at a thin layer of lithium, and they watched what came out. When a proton hits a lithium nucleus, it can stick. The result is a nucleus of beryllium, and it arrives in a state of high excitement, holding far more energy than it wants to hold. Physicists call this an excited state, and it is exactly what it sounds like. The nucleus is jangling, buzzing, desperate to calm down, so it dumps the excess. Usually it does this the boring way, by spitting out a photon and settling into its ground state. Occasionally it does something more interesting. Instead of releasing one photon, it converts that energy directly into a pair of particles, an electron and its antimatter twin, a positron. They fly out of the nucleus together in opposite directions and then curve away from each other. Here is the part that matters, and it is the whole experiment in one sentence. The angle between them is predictable. Physics knows exactly how often those pairs should come out at a wide angle versus a narrow one. The prediction is a smooth curve, lots of pairs at small angles flying nearly side by side, fewer and fewer as the angle opens up. By the time you get to a wide separation, the count should have dropped away to almost nothing, falling off smoothly, like the side of a hill. The Hungarian team built a spectrometer to measure that hill. Detectors arranged in a ring around the target, catching electron and positron pairs, tallying the angle between them, one event at a time, for months. The hill came out exactly as predicted, falling, falling, falling. And then, at about 140 degrees, roughly the angle your arms make when you throw them wide open, the count went back up. A bump. A small hill sitting on the side of the big one, where the ground was supposed to be flat and empty. There is only one way in ordinary physics to make a bump like that. If the nucleus, instead of converting its energy directly into a pair, first made a real particle, and that particle then flew a tiny distance and decayed into the pair, the geometry changes completely. A particle with mass has a preferred angle. It stamps its signature onto the way its children fly apart. Heavy particle, wide angle. Light particle, narrow angle. The bump was the signature of something with mass. Something being born inside a beryllium nucleus, living for an unimaginably short instant, and dying into an electron and a positron. The team ran the numbers backwards from the angle to find the mass of whatever was making the bump. The answer came out at about 17 million electron volts, roughly 33 times the mass of an electron, something like 1/50th the mass of a proton. They had no idea what could possibly live there, because that particular mass is one of the emptiest addresses in all of physics. To understand why the Hungarian result caused such a commotion, you have to understand the neighbourhood where it landed. Physics has a map of every particle it knows. Arrange them by mass, from lightest to heaviest, and you get a strange and lumpy landscape. Down at the bottom sits the photon, weighing nothing at all. Just above it, neutrinos, so light that their masses are still being argued over. Then the electron, the lightest thing with any real weight to speak of. At the top of the map, the giants. The Higgs boson, 125 billion electron volts. The top quark, heavier still, weighing about as much as an entire atom of gold despite being a single point with no size at all. Between the electron and the next thing up, there is a stretch of open country. The 17 million electron volt address sits right in the middle of that country. Above it, the next real resident is the muon, a heavy cousin of the electron at about 106 million. Below it, nothing but the electron and the photon. So the bump in Debrecen was pointing at a house, in a place where the map says there are no houses. That emptiness cuts both ways, and this is what makes the story so hard to settle. On one hand, an empty address is exciting. A new particle at 17 million electron volts would be the first genuinely new resident of the map since the Higgs, and it would be sitting in territory so unfashionable that almost nobody had thought to look. On the other hand, an empty address is suspicious, because that region is not unexplored. It is one of the most thoroughly worked over energy ranges in the history of the field. Consider what has already passed through it. Every nuclear reactor built since the 1940s has been flooding its surroundings with particles at exactly these energies. Every medical isotope, every radioactive decay in every rock on Earth, every cosmic ray shower has been depositing energy in this range for as long as the universe has existed. More to the point, particle physicists have been colliding electrons and positrons at these energies since the 1960s. They have measured the magnetic properties of the electron to 12 decimal places, a precision so fine that it would detect a discrepancy the width of a human hair across the diameter of the Earth. A new particle at 17 million electron volts would leave fingerprints on that measurement. So whatever made the bump has to be extremely shy. It has to be able to be produced inside a beryllium nucleus, often enough to make a visible hill in the data, and then it has to hide from every other experiment in 80 years of nuclear physics. That is a brutal set of requirements. Shy enough to have escaped everyone, loud enough to be seen in a modest lab in Hungary. Almost every simple explanation dies against that wall. The plain, dark photon, the one we built up over the last 3 chapters, dies first. A dark photon at that mass would show up in the decay of a particle called the neutral pion, and an experiment at CERN had already looked at that decay with enormous care and found the space empty. So the theorists went to work, and within months they produced a solution. It was clever, elegant, and deeply weird. The particle would have to be blind to protons. The fix has a name that sounds like a joke, and the joke stuck. Physicists call it protophobic, afraid of protons. To see why anyone would propose something so strange, you have to see what killed the simple version first. Take a neutral pion. It is one of the most common particles produced in any collision. A fleeting bundle of quarks that lives for less than a billionth of a second and then decays, almost always, into 2 photons. If a dark photon existed at 17 million electron volts, a pion could occasionally decay into 1 ordinary photon and 1 dark photon instead, and the dark photon would then turn into an electron and a positron. So the pion would produce a photon and a pair, with the pair carrying that exact mass. An experiment at CERN called NA48 had studied pion decays by the hundreds of millions. They looked. That signature does not exist, down to a level far below what a dark photon would produce. The simple explanation was dead within weeks of the Hungarian announcement. Then a team of theorists in California, led by a physicist named Jonathan Feng, noticed something about the coupling. The pion is made of a quark and an antiquark, an up and an anti-up, mixed with a down and an anti-down. When a pion decays into a photon, the strength of that decay depends on the electric charges of those quarks. Change the charges the new particle responds to, and you change how often the pion makes it. And there exists one specific combination of charges where the pion contribution cancels out, almost perfectly. The 2 pieces of the pion contribute with opposite signs, and if the new force couples to up quarks and down quarks in just the right ratio, the pieces annihilate each other, and the pion goes silent. That particular combination has a name in plain language. It means the new force barely notices a proton, and it speaks clearly to a neutron, which is enough to explain everything at once. Beryllium nuclei are packed with neutrons, so the new particle gets made there. Pions cancel it out, so the CERN experiment sees nothing. Every high-precision measurement built around electrons and protons stays untouched. Take a moment with how bizarre this is. Every force we know treats a proton as a loud object. The electric force sees a proton as a full unit of positive charge, the loudest thing in the atom. The strong force grips its quarks. Gravity feels its mass. This proposed force would look straight through a proton as though it were empty air while feeling a neutron perfectly well, even though a neutron carries no electric charge at all. The critics pounced immediately, and their objection was fair. This looks like a solution engineered backwards from the answer. You start with a signal you want to keep and a pile of experiments you need to dodge, and you tune your particle until it threads the needle. Physics has a long history of theories built this way, and most of them are wrong. The defenders had an answer. The needle threading was not free. Once you fix the couplings to make the pion cancel, the theory makes hard predictions everywhere else. It cannot be tuned again. It either survives the next test or it dies. The next test came from an unexpected direction. The same laboratory in Hungary went looking for the bump in a completely different nucleus. If the bump in beryllium was a fluke of one experiment, one nucleus, one set of detectors, then it should never appear anywhere else. So the Hungarian team did the obvious thing. They changed the nucleus. In 2019, they aimed their proton beam at a target that produces excited helium instead. A completely different nucleus. Different protons, different neutrons, different internal structure, different energy released when it settles down. The energy of the transition was higher. The angles worked out differently. Everything about the experiment shifted. The bump came back. And here is the thing that made theorists sit up. If the bump was some artifact of the detector, a quirk of geometry, or a miscalibration, it would appear at the same angle regardless of the nucleus, because the angle is a property of the machine. It did not appear at the same angle. It appeared at a different angle, because the helium transition releases a different amount of energy. Run that different angle backwards to find the mass of whatever made it, and you get the same answer as before. About 17 million electron volts. Then they did it a third time with carbon and got the same mass again. 3 nuclei, 3 different energies, 3 different angles, 1 mass. That is either a real particle or it is a coincidence so specific that it is hard to describe. The physics community split, and the split was sharp. One camp said this is exactly what discovery looks like. A signal that reproduces across independent conditions, always pointing back to the same underlying quantity, is the classic fingerprint of something real. It is how the Higgs was found. It is how almost everything is found. The other camp raised an objection that has never gone away, and it has nothing to do with the mathematics. Same laboratory, same team, same spectrometer, same analysis software, same choices about how to subtract the background from the data. If something in that chain has a subtle flaw, then it will produce a consistent wrong answer across every nucleus you point it at. Consistency proves that the flaw is stable. It says nothing about whether the flaw is real physics. There was a particular worry about the background. The smooth hill underneath the bump is itself a calculation, based on assumptions about how the nucleus behaves. Get that calculation slightly wrong at the edges, and you can manufacture a bump out of nothing, and it will look beautifully solid. This is the moment where science stops being about cleverness and becomes about something harder. Someone else has to look, with different hardware, in a different country, with different assumptions, and with every reason to want a different answer. 2 teams took up the challenge, on opposite sides of Europe. One of them was built to hunt something else entirely, and it had the sharpest eyes on the continent. It found nothing. Before the sharpest eyes weighed in, a smaller and stranger confirmation arrived, and almost nobody outside the field noticed it. It came from Vietnam. At the University of Science in Hanoi, a team decided to look at the same beryllium transition that started everything. They had a different machine, and the difference mattered enormously. The Hungarian spectrometer catches pairs across a wide sweep of angles at once, tallying everything that arrives. It is efficient. It is also complicated, because the detector's response changes across that sweep, and you have to model it precisely. The Vietnamese team used a two-arm design instead. 2 detectors positioned to catch one electron in one arm and one positron in the other, at a specific angle. Then you move the arms and measure again. Then you move them again. It is slow. It is tedious. It is also almost impossible to fool with a geometry error, because you are measuring one angle at a time instead of trusting a model of the whole sweep. In early 2024, they reported their result. They saw the anomaly. A different country, a different machine, a different philosophy of measurement, and the bump was there, at the same place, in the same transition. For the people who had spent 9 years defending the Hungarian result against accusations of a broken detector, this was the moment they had been waiting for. You cannot blame one lab's spectrometer for something that shows up in a completely different spectrometer. The caution came fast, and it came from within the community rather than from outside it. Both experiments were nuclear physics measurements of the same reaction. That means they share more than hardware. They share the theory that predicts the smooth hill underneath the bump. They share assumptions about how the beryllium nucleus is put together and about how its energy converts into pairs. When 2 experiments share their assumptions, their errors are correlated. A flaw in the shared theory shows up identically in both, and no amount of independent hardware will catch it. There was a real fear that the field was measuring the same mistake twice and calling it a confirmation. What everyone actually wanted was something else entirely. A test that did not involve nuclei at all. Because a nucleus is a mess. It is dozens of protons and neutrons swirling in a soup of strong force, a many-body problem that nobody can solve exactly, only approximate. Every prediction about what should come out of a nucleus carries a fog of uncertainty around it. A particle physics experiment carries no such fog. You make one particle hit one other particle. Nothing to approximate, nothing to model. If the new boson exists, it will appear on its own terms, naked, with no nucleus wrapped around it. 2 experiments were building exactly that. The first to report was in Switzerland, and it was designed to be merciless. At the Paul Scherrer Institute in Switzerland sits a detector that was never intended for this hunter tool. It was built to catch a muon doing something forbidden. A muon is a heavy electron, and when it dies, it decays into an electron and 2 neutrinos. The standard model says it can never decay into an electron and a photon. Never. The prediction is essentially 0. So a whole experiment was built to watch muons die, billions upon billions of them, looking for one single forbidden decay. To do that, it needed to be extraordinarily good at one specific thing: catching electrons and positrons and measuring exactly where they came from and where they went, which is precisely the skill the Hungarian anomaly demanded. The Swiss team realized they were sitting on the perfect instrument. They took their detector, aimed a proton beam at a lithium target, and reproduced the exact reaction that started everything a decade earlier. Same nucleus, same transition, same energy. A detector built by people with no stake in the outcome, using technology from an entirely different branch of physics, with a resolution the original experiment could not touch. They ran. They analysed. In 2024, they published. They saw nothing. The hill fell away smoothly, exactly as ordinary physics predicts, with no bump sitting on it anywhere. They set a limit instead. If the particle exists and is produced in that transition, it happens less often than about 1 time in 100,000 of those decays, below the level the Hungarian result requires. A physicist on the team put it carefully, and the care is worth noticing. The result does not close the case. It weakens the simplest interpretations. That is the language of someone who understands the trap. Because a null result is a strange animal. The Swiss experiment was more precise than the Hungarian one in almost every respect, and it still could not deliver a clean kill. The 2 experiments were not measuring identical things. The way the proton beam energy is tuned, the way the target is prepared, the specific mixture of nuclear states that gets excited, all of it differs, and all of it can shift how often a new particle would be produced. There is even a version of the theory where both results survive, because the production rate depends on how the beryllium nucleus is excited, and the two beams excited it differently. This is what physicists mean when they say an anomaly is hard to kill. Every null result has a crack in it. Every crack has a theorist willing to live inside it. So the field waited for the other test, the one with no nucleus at all. It was in Italy. It had been running for 3 years. And when it finally reported, it did not confirm the anomaly, and it did not kill it. It did something worse. At Frascati, just outside Rome, there is a small accelerator and an experiment with an unusual idea. The idea is to make the particle out of nothing but light and antimatter. Here is how it works, and it is the cleanest thing in this entire story. Take a beam of positrons, antimatter electrons, fire them at a target made of a very thin diamond wafer. Inside that wafer are ordinary electrons sitting in their atoms, going about their business. A positron meets an electron. They annihilate. Both particles cease to exist, and all of their mass and energy is converted into pure energy at a single point. That energy has to become something. Usually it becomes 2 photons and the story ends. But if you tune your positron beam to exactly the right energy, something else can happen. The energy released can match the mass of a new particle precisely, and when the numbers line up exactly, the universe stops being reluctant. Physicists call this resonance, and you already understand it from music. Sing the right note near a wine glass and the glass rings. Sing a note slightly off, and nothing happens at all. The response is not gradual. It is a spike, sharp and narrow, at one exact frequency. The energy of the positron beam is the note. The new particle is the wine glass. So the team scanned. They set the beam energy, collected data, nudged it up, collected data, nudged it again. Walking across the region where the Hungarian anomaly said the particle should live, one tiny step at a time, listening for the glass to ring. The beauty of this is that there is no nucleus anywhere in the argument. No many-body problem. No fog of approximation. One positron, one electron, one clean annihilation, and a resonance that either exists or does not. The scale of it is hard to picture. Over 500 billion collisions collected in 2022. Then came 3 years of analysis, and the team did something that deserves respect. They ran it blind. The physicists analysing the data were prevented from seeing where their own signal would appear, until every decision about the analysis was locked in. You cannot fool yourself into finding a bump if you are forbidden from knowing where to look for it. They finished. They unblinded. There was an excess. Sitting at the energy the Hungarian anomaly predicted. In a machine with no nuclei, no shared assumptions, no connection to Debrecen except the number itself. And it was small, 2 standard deviations. In some analyses, a little less. The one thing everyone wanted was a clean answer, and what they got instead was a signal sitting in the exact zone where physics goes to argue with itself for a decade. To understand why a 2 sigma result is so agonizing, you have to understand what physicists are actually afraid of. They're afraid of themselves. Here is what 2 sigma means, in plain terms. If there is no particle at all, and the universe is just noise, then a bump this big or bigger will appear by pure luck about 1 time in 20. 1 in 20. Flip a coin 4 or 5 times in a row and get all heads, and you've done something about that unlikely. You would not call it a discovery, you would call it a Tuesday. Now consider how many measurements the field makes. Thousands of experiments, each producing thousands of plots, each plot containing dozens of places where a bump could randomly appear. With that much data being generated, 1 in 20 flukes are not rare events, they're a constant rain. This is why the standard for discovery in particle physics is 5 sigma, and 5 sigma is not a small step up from 2. It corresponds to roughly 1 chance in 3.5 million. The distance between 2 and 5 is not a hop, it is a canyon. Physics learned this the hard way, and the graveyard is well populated. In 2015, both giant detectors at the Large Hadron Collider saw a bump in the same place, at 750 billion electron volts in photon pairs. 2 independent experiments, 2 independent teams, the same signal at the same place. 500 theory papers were written about it in 8 months. Careers pivoted, conferences reorganized, more data came in. The bump evaporated completely. It had been noise the whole time, and the fact that 2 experiments saw it together was itself just luck. That memory hangs over every conversation about the Hungarian anomaly, and yet, there is something the skeptics have to explain, and it is genuinely awkward for them. The Italian excess landed at the same mass as the Hungarian one, not near it, at it, and the Italian experiment measures that mass with far more precision than a nuclear experiment can, because it is set directly by the energy of the beam, a quantity you can know almost perfectly. A random fluke has no reason to land there. It could have landed anywhere across the scanned range. So the field is stuck in the worst possible place. The evidence is too consistent to dismiss and far too weak to accept. Serious people have run the combined analysis, pulling every measurement together, and the answer that comes out depends heavily on assumptions about how the errors in different experiments relate to each other, which nobody can settle. The Italian team is upgrading their machine and taking more data now. That will help. But there is an explanation nobody wants to talk about, sitting quietly in the corner of the room, and it is the least exciting possibility of all. Maybe there is no particle. Maybe the nucleus is just harder than we think. Every good mystery has a suspect. Nobody wants to be guilty, because the truth would be dull. In this story, the dull suspect is the beryllium nucleus itself. Think about what that nucleus actually is. 4 protons and 4 neutrons bound together in a knot of the strong force. 8 objects, each of them made of 3 quarks. Each of those quarks trading gluons at a rate that makes the interior of the nucleus one of the most violent environments in existence. Nobody can calculate that exactly. Nobody. The strong force at these energies is beyond exact solution, and every prediction about how a nucleus behaves is an approximation built on a model built on assumptions. Now remember what the anomaly actually is. It is a small bump sitting on top of a smooth predicted hill. The bump is only a bump relative to that predicted hill. If the hill is slightly the wrong shape, the bump appears for free out of nothing, with no new physics anywhere. Theorists have gone looking for ways to bend the hill. One idea involves interference. The excited beryllium nucleus does not have to decay through one clean route. There can be multiple quantum paths to the same final electron and positron pair, and quantum paths add together like waves. Add 2 waves and you get places where they reinforce and places where they cancel. The result is a rippled surface rather than a smooth slope. Get the interference between those paths slightly wrong in your model, and you can produce a lump in the angular distribution at a wide angle, exactly where the anomaly lives. Another idea concerns the shape of the nucleus. Beryllium-8 is famously strange. It is essentially 2 helium nuclei stuck together in a dumbbell, wobbling, about as far from a neat sphere as a nucleus gets. That dumbbell shape affects how energy converts into particle pairs, and the standard calculations were built for rounder objects. There are more of these papers than you would expect, and none of them has been able to produce the bump convincingly, which is a point in favour of new physics. The honest position is uncomfortable. The nuclear explanations have never quite worked. They also have never quite been ruled out, because the calculations are hard enough that a determined skeptic can always find another corner to hide in. So the whole edifice rests on one thing: whether the smooth hill in the original data was drawn correctly. 10 years, 4 nuclei, 3 continents, 2 experiments finding it, 1 finding nothing, and a nuclear theory too tangled to settle the argument. This is what a live scientific question looks like from the inside. It looks like a mess for a decade, and then one day it resolves, and everyone writes a story pretending the answer was obvious all along. The field had seen this movie before. There was another anomaly, much bigger, much older, much more famous, and physicists had been telling the world for 20 years that it was the best evidence for a fifth force ever found. It was about to fall apart in the most humiliating way possible. Take a muon and put it in a magnetic field. A muon is a heavy electron. It weighs about 200 times more, and it lives for about 2 millionths of a second before it decays. It carries electric charge, and it spins. Anything that spins and carries charge behaves like a tiny magnet. Put a tiny magnet in a big magnetic field, and it does what a spinning top does when you tilt it. It wobbles. Physicists call it precession, and the speed of the wobble is the measurement. Here is why that wobble became the most important number in physics for 20 years. The speed depends on the muon, and the muon is never alone. In quantum mechanics, empty space is a boiling foam. Particles flicker into existence around the muon constantly, borrowing energy from nothing and paying it back before the universe can object. Electrons and their antimatter twins, photons, quarks, everything. Each of those flickering ghosts nudges the muon's magnetism a tiny bit, so the speed of the wobble contains a sum over every particle that exists. Every particle that exists, including the ones we have never found. That is the trap that makes the measurement so powerful. If there is a fifth force out there, and it speaks to muons at all, then dark photons are flickering around every muon in the universe right now, and their contribution is baked into the wobble. You do not need to produce the particle, you just need to measure the wobble precisely enough to notice a discrepancy, and then you know something invisible is out there. So they measured it, at Brookhaven in New York starting in the 1990s, and the answer came out wrong, slightly, stubbornly. The muon wobbled a hair faster than the theory said it should. The gap was tiny, out in the 9th decimal place, and it refused to go away. For 20 years, that gap was the single best evidence that the standard model was incomplete. Thousands of papers were written explaining it. Dark photons were among the favourite explanations for a while. The gap was a lighthouse, and the whole field steered toward it. The measurement moved to Fermilab, outside Chicago, and the move itself was an epic. The magnet ring is 50 feet across and cannot be taken apart without destroying it. So they put it on a barge, floated it down the east coast of the United States around Florida up the Mississippi, and then drove it across Illinois at night on a truck at 15 miles an hour with police escorts, while thousands of people came out to watch a giant white ring roll past their houses in the dark. They rebuilt it. They ran it for 6 years. In June of 2025, they published their final answer, precise to 127 parts per billion. It was the most precise measurement of its kind ever made, and by the time it arrived, the thing it was supposed to test had quietly vanished. The theory had moved. The gap between theory and experiment had two sides, and everyone had been watching the wrong one. The experimental side was hard, and the physicists made it look easy. The theory side was where the trouble lived. To predict the wobble, you have to add up the contribution of every flickering ghost around the muon. Most of those are easy. Photons and electrons are clean, and physicists can calculate their effect to a precision that beggars belief. Then there are the quarks. When a quark flickers into existence near a muon, it drags the strong force in with it, and the strong force at low energies is unsolvable by ordinary methods. The equations tangle into themselves and refuse to yield. This one piece, the hadronic contribution, was responsible for almost the entire uncertainty in the prediction. And for decades, there was only one way to get it. You measured it instead of calculating it. You took data from other experiments, where electrons and positrons collide and produce quarks, and you used those measurements as a stand-in. Feed the data in, and out comes the number. That is where the gap came from. Then a second method matured, lattice quantum chromodynamics. You give up on solving the equations and simulate them instead, chopping space and time into a grid of points and grinding the strong force out on the largest supercomputers on Earth, using tens of millions of processor hours for a single number. In 2020, a European group published their lattice answer. It disagreed with the data-driven method, and it agreed with the experiment. If the lattice was right, the gap had never existed. 20 years of excitement had been a bookkeeping problem. The fight that followed was brutal and lasted 5 years. Other lattice groups checked. They found the same thing. Then a Russian experiment measuring the input data got a different answer than everyone else, which meant the data-driven method was fighting itself as well. In May of 2025, the international theory group that arbitrates this question published its verdict. They abandoned the data-driven approach as their recommendation and adopted the lattice result. Their new prediction disagreed with their own previous prediction by 3 standard deviations. The theory had moved further than the anomaly it was supposed to explain, and it landed on top of the experiment. Weeks later, Fermilab published its final, magnificent 6-year measurement, and it agreed with the standard model. The lighthouse had switched off. Sit with what happened here. because it is the most important lesson in this entire hunt. For 20 years, the best evidence for a fifth force was real, published, peer-reviewed, and confirmed by multiple experiments. Every part of the story was honest, every measurement was correct, and the anomaly was in the arithmetic. Which is exactly why nobody will accept a bump from a Hungarian spectrometer without a fight. The muon taught the field at enormous cost that when a measurement and a theory disagree, the theory is a suspect too. So the field made a decision. Stop chasing whispers and calculations, go make the particle, and if it will not come to you, then you fire a beam of electrons into a solid block of metal and wait for something to go missing. There is an experiment at CERN that hunts a particle it can never see, using a method that sounds like cheating. It watches for energy that disappears. The setup is almost crude in its simplicity. Take an electron and accelerate it to 100 billion electron volts. Aim it at a block of lead and plastic layered like a sandwich, which is also a detector. The electron slams in and shatters into a shower of photons and more electrons, and the block measures every scrap of energy that shower deposits. Then you check the arithmetic. Energy in, energy out. 100 billion goes in. 100 billion should come out spread across the shower. Almost always it does. The books balance, event after event, billions of times. Now suppose that as the electron crashes into a nucleus in that block, it radiates a dark photon. The dark photon is barely coupled to anything, so it does not shower. It does not deposit. It flies straight out the back of the detector, through the walls, through the concrete, through the hill, and it never comes back. Then the books do not balance. You get an event where a full energy electron went in, and only a fraction of that energy shows up in the block. The rest is simply gone. That is the entire signal, a hole in the accounting, and the reason this method is so beautiful is a matter of raw statistics. Older experiments tried to catch the dark photon by waiting for it to decay back into visible particles somewhere downstream. That requires two rare things to happen in a row, first the production, and then the decay, and the chances multiply into near impossibility. Watching for missing energy requires only the first rare thing. You give up on ever seeing the particle. In exchange, you get a sensitivity that is millions of times better. The cost is paranoia. Because energy goes missing for boring reasons all the time. An electron scatters sideways and slips out a gap in the detector. A neutron sneaks past and carries energy away unnoticed. A stray particle in the beam gets mistaken for an electron. Any of these produce exactly the signature you are hunting. So the experiment is built as a fortress of vetoes. Detectors in front to confirm the incoming electron is real and has the right momentum. A wall of counters behind the target to catch anything trying to escape. A hadron calorimeter after that, to catch anything that got past the first wall. The goal is a state that physicists describe with a phrase that sounds impossible. Background free, meaning that across the entire run, the expected number of fake events is less than 1. They collected nearly 1 trillion electrons on that target between 2016 and 2022. The books balanced. Every single time, 0 events. No dark photon in the range they could reach, which is now the strongest limit anywhere below 1/3 of a billion electron volts. That result did something specific and important. Combined with a similar search in California, it ruled out the invisible dark photon as the explanation for the muon wobble, years before the wobble dissolved on its own. And it walked straight into the shaded region where cosmology says the portal should be. It found the region empty, so far. Most searches in physics are a hunt across an open field. This one has a target painted on it, and the paint came from the Big Bang. Here is where the bullseye comes from. Rewind the universe to the first microsecond. Everything is packed together and unimaginably hot, and at that temperature the portal is wide open. Energy is so plentiful that ordinary particles are constantly making dark ones, and dark ones are constantly annihilating back into ordinary ones. The two worlds are in a furious equilibrium, trading population back and forth, perfectly balanced. Then the universe expands. Think of a crowded room where everyone is paired up and vanishing on contact. As long as the room is packed, every particle finds a partner instantly, and the population drops. Now start stretching the walls. The crowd thins. Partners get harder to find, and at some point a particle can wander for the rest of time without ever bumping into its twin. The annihilation stops. Whatever is left in the room is left forever. Physicists call this freeze-out, and it is the single most important idea in dark matter theory, because it turns a philosophical question into arithmetic. The amount left over depends entirely on how easily the particles found each other. Strong coupling means they kept annihilating well into the expansion, and almost nothing survives. Weak coupling means they gave up early, and the room stays crowded. Now flip the logic around, because this is the moment the whole thing becomes a science. We know how much dark matter is left over. We have measured it. The Planck satellite mapped the afterglow of the Big Bang across the entire sky and read the density of dark matter out of the pattern of hot and cold spots. The number is solid to within about 1%, so we know the answer at the end of the calculation, which means we can run it backwards and solve for the beginning. Do that, and out comes a specific value for the strength of the portal. Not a range, a line. A thin curve drawn across the map of possibilities, telling you that if dark matter got here the way we think it did, and if the dark photon is the door it came through, then the leak has this size at this mass exactly. Physicists call it the relic target, and it changed the character of the entire field. Before it, dark sector searching was a matter of taste. You picked a coupling, you built a machine, and you hoped. After it, there was a place to stand. The number lands in a merciful spot, around 1 part in 10,000, for dark particles weighing between about 1/millionth and 100th of a proton. That is reachable. That is a beam of electrons and a block of metal, rather than a machine the size of a mountain range. Which brings us back to that block of metal at CERN and to the thing that should be keeping people awake. The near trillion electrons fired into that target pushed the search across the relic line for the simplest versions of the model. Scalar dark matter in a wide band of masses ruled out. Majorana dark matter ruled out across a similar stretch. The line is being crossed, and the room behind it is empty. There is a version of this story where the portal simply is not there, and the sky is telling us something we do not know how to hear yet. There is another version where the door exists and we have been standing at the wrong one, because a beam dump only sees the dark sector if the dark sector holds still, and the biggest machine on Earth had been running a completely different kind of search for years, using a trick that nobody thought would work. The Large Hadron Collider was built to hunt giants, and one of its 4 detectors decided to hunt something feeble instead. The detector is called LHCb, and it sits in a cavern on the French side of the ring. It was designed to study a particle called the Beauty quark, which meant it had to be exceptionally good at one skill, seeing exactly where a particle was born. That skill turned out to be the key to a completely different hunt. Picture what happens when 2 protons collide at the LHC. The energy is so extreme that the collision sprays out hundreds of particles in a fraction of a nanosecond. It happens 40 million times a second. The detector is drowning. Somewhere in that flood, occasionally a dark photon could appear, and unlike the invisible version that flies out of a beam dump, this one might decay into something we can see. 2 muons flying apart, carrying between them the exact mass of the thing that made them. So the search is simple to state. Take every pair of muons the machine ever produced, add up their masses, look for a spike. The trouble is that the universe already makes muon pairs constantly, through completely ordinary processes, in numbers that dwarf anything a dark photon could contribute. You're listening for a whisper inside a stadium. The team did 2 things that made it possible. First, they threw away the concept of saving data. The detector produces vastly more information than any storage system on Earth could hold, so traditionally you keep the interesting events and discard the rest. LHCb rebuilt itself to reconstruct every collision fully, in real time as it happened, and make the decision instantly. That let them keep muon pairs that any other experiment would have thrown in the bin. Second, they used geometry as a filter. A feebly coupled particle lives longer than a strongly coupled one. It is shy, so it takes its time deciding to decay, which means it drifts. It might travel a few millimeters from the collision point before it dies. That drift is everything. An ordinary muon pair springs from the exact point where the protons met. A dark photon pair springs from a spot slightly off to the side, a tiny displaced scar in the middle of the chaos. LHCb can see that scar. It can resolve where a particle decayed to within a fraction of a millimeter, in an environment where hundreds of tracks are crossing each other. So they looked. Across billions of collisions, At every mass from a fraction of a proton up to several times a proton's weight, the spike is not there, anywhere. The limits they set on the leak, combined with results from a Californian experiment and from the giant detectors on the other side of the ring, now exclude the leak above roughly 1 part in 1,000 across most of that range, which leaves the field in a strange position. The middle of the map is being cleared. The bottom is being approached from below by beam dumps. The dark photon is being squeezed into a corner. And then a small group of physicists pointed out that everyone had been looking in the wrong direction for 40 years. Sideways. The insight that led to it is embarrassing in its obviousness, and it took 30 years for anyone to say it out loud. Every detector at every collider is built around the collision point in a barrel, layers wrapped around the beam pipe like the rings of a tree, catching whatever flies out sideways. There is a reason for that. Heavy particles come out sideways. When you smash 2 protons together and something massive is created, it emerges with a lot of momentum perpendicular to the beam, because it took a violent head-on hit to make it. Light particles do the opposite. A feeble, lightweight thing produced in a collision does not get kicked sideways. It gets carried forward, riding the momentum of the original beam, flying straight down the pipe in the direction everything was already going. And straight down the pipe is exactly where nobody was looking. It is where the beam goes. It is the one direction you cannot put a detector because the beam would destroy it. So a group of physicists asked a question that sounds like a joke. What is down there? The answer was a service tunnel. A shaft. Unused. About a quarter of a mile downstream from one of the collision points, sitting almost exactly on the line of the beam axis. Between the collision and that tunnel lies about 300 feet of solid rock and concrete. That rock is the entire experiment. Anything ordinary produced in the collision slams into it and stops. Protons, muons, photons, the whole flood, absorbed. A feebly coupled particle strolls through it as though it were fog because it barely notices matter at all. So you put a small detector in the tunnel, aim it at the collision point through hundreds of feet of stone, and wait. Anything that arrives came through the rock, and almost nothing comes through the rock. They built it. It is called phaser, and it is tiny by the standards of the LHC. A cylinder about the length of a car sitting in a hole. It cost a rounding error compared to the detectors upstairs. It started taking data in 2022, and within a year it did something remarkable that had nothing to do with dark photons. It caught neutrinos produced in a collider for the first time in history. Particles that everyone knew were being made by the millions, streaming out of every collision since the machine turned on, and flying into the dirt unrecorded for a decade. Then it turned to the hunt. It looked for a dark photon flying forward out of the collision, surviving the trip through the rock and decaying inside the detector into an electron and a positron. It found nothing. It set limits in a region no other experiment could reach, in the small corner where the particle is light enough and shy enough to survive the journey. The lesson stings. For 40 years, the most powerful machines humans ever built may have been manufacturing the answer in enormous quantities and firing it into the ground. The plans now call for something bigger down there. A whole facility, a cavern dug out for the purpose, filled with detectors staring back up the beamline. And while that gets designed, a theorist raised a hand and pointed out that all of these searches, the invisible ones and the visible ones alike, share a single assumption. Break it, and every result on the board becomes negotiable. Every search we have described splits the world in two. Either the dark photon decays into something we can see, and you hunt for the visible debris, or it decays into something we cannot, and you hunt for the missing energy. Visible or invisible. 2 strategies, 2 sets of experiments, 2 maps. Between them, physicists assumed they had the possibilities covered. Then someone asked what happens if the dark sector has more than one particle in it. Ours does. Our sector has electrons and muons and quarks and neutrinos, a whole zoo, arranged in a structure nobody fully understands. Assuming the hidden sector contains exactly one particle is an assumption of convenience. So suppose there are 2, a lighter dark particle and a slightly heavier one, almost the same mass separated by a small gap. Now watch what the dark photon does. Instead of decaying into 2 identical particles, it decays into one light and one heavy. Both are invisible, both fly out of the detector, except the heavy one is unstable. It has a little extra mass to shed, and the only way to shed it is to fall down to the light state and dump the difference. That difference comes out as an electron and a positron, carrying almost no energy, because the mass gap is tiny. And it takes its time. The heavier state can drift for meters before it decays. Look at what that does to the searchers. The missing energy experiment sees the dark photon carry the energy away, and calls it invisible. So far, so good. Except now, there is a soft electron pair appearing somewhere downstream, inside the veto system, and the veto system was designed to reject exactly that. The experiment throws away its own signal as background. The visible decay experiments have the opposite problem. They look for a clean pair carrying the full mass of the parent particle. This pair carries a sliver of it. The energy is wrong, the geometry is wrong, and the event fails every cut. The signal falls into the crack between two strategies. Physicists call this semi-visible decay, and it is a mathematically natural thing to build. It requires nothing exotic. It requires the dark sector to be slightly more interesting than the simplest possible version of itself. There is a version of this called inelastic dark matter, and it has a further property that is almost cruel. The dark matter particle can only scatter off ordinary matter by converting into its heavier partner. In the early universe, everything was hot enough for that to happen easily. Today, in a detector buried under a mountain, the dark matter drifting through has nowhere near enough energy to make the jump, so it cannot scatter at all. It passes through the most sensitive detectors humanity has built, and it is forbidden by its own structure from leaving a mark. The experiments have started fighting back. Teams have gone into their old data and reanalyzed it, deliberately keeping the events they used to reject, hunting for those soft displaced pairs. The results are limits again, weaker limits over a narrower range, in a model with more knobs to turn. This is the shape of the whole enterprise. Every time the searchers close a door, the theory grows a hallway, which is why a completely different community, working with lasers instead of accelerators, decided to stop asking nature to cooperate and simply try to build the particle out of light itself. Underneath Hamburg, Germany, there is a tunnel that used to hold a particle collider. The machine is gone. The tunnel remains, a concrete ring buried under the city and under a public park running for miles. And in one straight stretch of it, physicists built the strangest experiment in this entire story. They are trying to shine a laser through a solid wall. The setup, described plainly, sounds like a magic trick. Take a long line of superconducting magnets, more than 300 feet of them, salvaged from the dead collider and cooled to a few degrees above absolute zero. Fire a laser down the middle of them, then put up a barrier, solid, opaque. Light stops there completely. On the far side, another 300 feet of magnets, and at the very end, a detector. The claim is that light will appear on the other side of the wall. Here is why that is a serious proposal rather than a stunt. Go back to the mixing. Our photon and the hypothetical dark photon are stirred together, which means the thing we call a photon is a blend. And a blend of two things with different masses does something remarkable. It oscillates. The photon travels along, and because it is partly the other thing, it can slide over and become the other thing entirely. Then slide back. It flickers between identities as it flies, like a coin tumbling in the air, and the rate depends on the mass difference and the size of the leak. So consider a photon in the first magnet string. It tumbles. At some point during its journey, it happens to be in its dark state. Then it hits the wall. The wall stops photons. The wall means nothing to a dark photon. It sails through the barrier without slowing down, carries on into the second magnet string, keeps tumbling, and somewhere in there it flips back into ordinary light. Light appears on the far side out of a wall that nothing crossed. The magnets are there because for some candidate particles, the conversion needs a magnetic field to happen. For a dark photon, the field is unnecessary, and the same apparatus tests both. The odds are appalling. The chance of a single photon converting, crossing, and converting back is roughly the leak raised to the fourth power. If the leak is 1 part in a million, the round trip is 1 part in a million. So you cheat with numbers. You send an absurd quantity of photons, and you trap them. They built optical cavities, mirrors at each end of the magnet string so the light bounces back and forth thousands of times before it escapes, multiplying the effective power enormously. The storage time they achieved sets records. A single photon rattles in there for milliseconds, which sounds brief until you realise it has crossed the entire length of the experiment tens of thousands of times. Then they did something even stranger to the second cavity. They tuned it so that the regenerated light, if it exists, builds up in resonance too. 2 cavities, 1 wall, a laser. Miles of tunnel under a park where people walk their dogs. They turned it on in 2023, and after a year of calibration they ran their first real science campaign. Then came the hard part, detecting a signal so faint that the word faint stops meaning anything. The signal they were hunting arrives at a rate of roughly 1 photon per day. Sit with that. The most powerful laser system available, trapped in a mirror cavity, bouncing tens of thousands of times, and the expected output on the far side of the wall is 1 particle of light in 24 hours. Now consider what 1 photon per day looks like as a power measurement. It is around 10 to the minus 24 watts, a quadrillionth of a trillionth of a watt. Your phone screen puts out about a watt. A firefly, roughly 1,000th of a watt. The experiment needed to measure something a billion times fainter than an insect glowing in a field. There is no detector that simply does this, so they built the measurement out of interference instead. The method is called heterodyne detection, and the idea is borrowed from radio. You take a second laser, a reference beam, and you overlap it with whatever might be coming out of the wall. If a regenerated photon is there, the 2 beams beat against each other, the way 2 slightly mistuned guitar strings produce a slow throb. The throb is at a frequency you chose in advance, so you know exactly what note to listen for, which means you can average over months and dig a signal out of noise that swamps it by orders of magnitude. The catch is that the 2 lasers have to be locked together with insane precision. The frequency control they needed is measured in fractions of a millionth of a cycle per second, on light that oscillates hundreds of trillions of times a second. That is like 2 people on opposite sides of the planet agreeing on the length of a year to within a millionth of a second, and holding that agreement for weeks. They did it. The first science campaign ran from February to May of 2024, and after more than a year of analysis, they published in December of 2025. No light came through the wall. The limit they set on lightweight particles coupling to photons improved on every previous experiment of this kind by more than a factor of 20. They set constraints on scalars, on vectors, on tensors, on every shape a new particle could take. And there is something in that result that matters more than the number. Every other constraint in this story leans on something outside the laboratory. Beam dump results depend on models of how particles are produced in nuclei. Astrophysical limits depend on how a star works. Cosmological limits depend on the history of the universe. The wall experiment depends on none of it. Photons in, photons out, in a tunnel under Hamburg. If the universe surprises us about how stars burn or how the early cosmos evolved, this measurement does not flinch. The team calls it model independent, and in a field built on assumptions stacked on assumptions that is worth more than sensitivity. They are upgrading now. Better mirrors, a better detector, a target sensitivity 1,000 times beyond where they started. Meanwhile, on the other side of the Atlantic, another group had the same idea and made it stranger. They gave up on light entirely and started shouting through a sealed metal can. Outside Chicago, in a laboratory that builds particle accelerators, there is an experiment made of 2 metal cans. The cans are extraordinary objects. They are superconducting radio frequency cavities, machined from pure niobium, polished to an atomic smoothness, and cooled to about 2 degrees above absolute zero. They exist because they are the best containers for electromagnetic energy ever built. Put a radio wave in one, and it rings for a very long time. The energy bounces off the walls with almost no loss, billions of times before it fades. Physicists measure this with a quantity called Q, and these cavities reach values that beg a belief. A church bell struck once might ring for 10 seconds. Scale that up by the ratio these cavities achieve, and the bell would ring for years. Now the experiment: take 2 of these cans, fill one with radio energy, driven at about 1 1/3 billion cycles per second. That is the emitter. It is shouting. Put the second can next to it, sealed, empty, cold, and listening. That is the receiver. Between them, a shield. Metal. Radio waves cannot cross it. The whole point of a superconducting cavity is that electromagnetic fields stay inside, and the shield ensures that anything leaking out the emitter dies before it arrives. If ordinary physics is correct, the receiver hears silence forever. If the leak exists, the receiver hears a hum. Because inside the shouting cavity, the oscillating field is tumbling. Part of it converts into the dark field, which crosses the metal wall as though it were not there, enters the second cavity and converts back. The receiver rings with a signal that had no way in. The elegance is that both cavities are tuned to the same frequency. The receiver is not merely listening, it is resonating. A signal, 1 trillion times too weak to notice, arrives, and it arrives in time with the cavity's natural note, over and over, building up like a child pumping a swing. They ran it. And the calibration problem was almost worse than the measurement, because you have to prove that any signal you see could not have leaked through a seam, a cable, a crack in the shield. They found nothing. They set a limit on the leak down to about 1.5 parts in a billion, the best in the world for a narrow band of masses, from a device that fits in a room. The result came with a bonus that delights me every time I think about it. The same setup constrains something we do not usually question, the mass of the photon itself. We say the photon is massless. That is not a thing anyone proved. It is a thing nobody has ever managed to disprove, and this experiment, hunting a hypothetical twin, incidentally set one of the better laboratory limits on whether ordinary light has any weight at all. So the labs are closing in from every direction, beams, walls, cans, and then a small group of physicists ask the question that turns the entire hunt inside out. What if the dark photon is not the messenger at all? What if it is the dark matter? Everything so far has treated the dark photon as a courier, something you make in a collision, watch fly away and try to catch. Now flip it. Suppose the dark photon is not carrying a force to dark matter. Suppose the dark photon is the dark matter, the whole 5/6 of the universe, made of the twin of light. It sounds like a cheat, and the mathematics permits it under one condition. The particle has to be absurdly light, not 17 million electron volts. Try a millionth of an electron volt or a billionth. Mass is so small that calling these things particles stops making sense. Because at that mass, quantum mechanics does something dizzying. Every particle has a wavelength, and the lighter it is, the longer that wavelength grows. Push the mass low enough and the wavelength swells to the size of a room, then a city, then a solar system. At that point, the individual particles overlap so completely that they stop being particles at all. They merge into a single field, sloshing back and forth across the galaxy, oscillating at a frequency set by its mass. There would be no dark matter rain. There would be a dark matter tone, a field filling this room humming at a fixed note, and every cubic inch of space is participating. And through the leak, that hum touches our world. The dark field oscillates, and because it is slightly mixed with electromagnetism, it drives a faint electric field in step with itself. Everywhere. Inside your body, inside a shielded room, inside a metal box designed to keep every radio signal on Earth out. So the experiment writes itself. Build a room with walls that block all radio, put an antenna inside, listen. Anything you hear came through the wall. A team at a university in California did exactly this. An antenna, a shielded room, a low-noise amplifier, and a computer performing a Fourier transform on the signal, breaking it apart into millions of individual frequencies at once. The dark field's tone would sit in exactly one of those bins, sharp and pure, because the field oscillates far more steadily than any radio station. 9 days of listening. They searched a band of masses corresponding to radio frequencies between 50 and 300 million cycles per second. Their limit on the leak reached 6 parts in 1,000 trillion. Other groups run magnetometers in shielded rooms and reach further into ranges below that. Nobody has heard the tone. There is something haunting about the picture, though. Every one of these experiments is a person in a sealed metal room, in total electromagnetic silence, straining to hear a note that would be coming from everywhere at once, that has been sounding since the universe was young, and that passes through the shielding, the building, the Earth, and them. If it exists, they are standing in it. The labs cannot rule it out. Their reach is finite, but there is a detector out there vastly larger than anything on Earth, and it fired once in 1987, and physicists have been squeezing it for evidence ever since. On the 23rd of February 1987, a star exploded in a small galaxy near our own, about 168,000 light-years away. It was the closest supernova in 4 centuries, and for the first time in history the machines were ready. 3 detectors around the world, buried deep underground, caught a burst of neutrinos. 24 particles, arriving over roughly 10 seconds, hours before the light reached us. 24. That is the entire data set. It remains one of the most valuable measurements in physics. Here is why it matters for our hunt, and the logic is beautiful. When a massive star's core collapses, it becomes a ball of neutrons about 12 miles across, hotter than anything in the universe outside of the Big Bang. Almost all of the energy of that collapse, roughly 99%, comes out as neutrinos. They do not come out instantly. The core is so dense that even neutrinos, which pass through a light-year of lead, get trapped. They bounce and scatter their way outward, taking about 10 seconds to escape. 10 seconds? That is what the detectors measured. Now add a dark photon to the story. The core is a furnace of charged particles slamming into each other. If the leak exists at the wrong size, that furnace makes dark photons in enormous quantities. They are shy, so they do not get trapped. They fly straight out of the core, carrying energy with them in an instant. That is a hole in the bucket. Energy that should have taken 10 seconds to trickle out, as neutrinos leaves immediately in a form nobody detects. Drain enough of it, and the neutrino burst gets shorter. Instead of 10 seconds, you see 2 or 1. We saw 10. So the dark photon cannot be draining that star, and that single fact, from 24 particles caught in a tank in Japan and a mine in Ohio, excludes a swath of the map that no laboratory on Earth can touch. There is a twist, and it is the best part. If the leak is too big, the dark photons stop escaping. They start interacting with the star's material, get trapped like the neutrinos, and deposit their energy right back where it came from. The star cools normally again, so the constraint has a floor and a ceiling. Too shy, and the particle never gets made. Too talkative, and it never gets out. The star only excludes the middle band. Above that band, laboratory experiments take over. Below it, nothing has ever been made. Physicists have been reworking this calculation for decades, and every few years someone finds a new subtlety in how a collapsing core behaves, and the limits shift. It is a measurement of a single event that nobody can repeat, resting on a simulation of the most extreme place in the universe, which is why the field would dearly love another supernova nearby. The next one will produce not 24 neutrinos but tens of thousands. Meanwhile, there is a star much closer that we can study every single day, and it may be manufacturing dark photons at this moment and firing them directly at your face. The Sun is a nuclear furnace with a core at roughly 27 million degrees, and it has been running for 4.5 billion years. If the leak exists, that core is a dark photon factory. The mechanism is unavoidable. The core is a plasma, a soup of bare nuclei and free electrons crashing into each other at furious speeds. Every time a charged particle accelerates, it radiates. That is how the Sun makes light in the first place, and because our photon is slightly the other thing, some fraction of that radiation comes out as the twin. Ordinary photons made in the core do not escape. They get absorbed and re-emitted so many times that the energy takes tens of thousands of years to wander from the center to the surface. The light hitting your skin today was made when humans were still living in caves. The dark photons leave in 8 minutes, straight out, through the entire mass of the Sun as though it were a window, which means there could be a flux of them pouring onto the Earth right now, from directly overhead in the day and up through the floor at night after passing through the whole planet. So build a telescope and point it at the Sun. That has been done. There are instruments, some using a spare magnet from a collider, that stare at the Sun through a magnetic field and watch for arriving dark particles converting back into ordinary photons inside the apparatus. They produce a beam of light out of an empty tube aimed at the sky. Nobody has seen it. The limits are strong. There is a second, subtler argument, and it constrains far more than any telescope. The Sun leaking energy through a hidden channel would burn differently. It would need to run hotter to hold itself up against gravity, which changes its structure, its size, and the neutrinos it produces. We measure all of those things with tremendous precision. Even better, run the same logic on other stars. There is a class of aging stars called horizontal branch stars, and their brightness and lifetime depend on how efficiently their cores hold onto energy. Astronomers count them in globular clusters, ancient balls of hundreds of thousands of stars orbiting our galaxy. If a hidden channel existed, those stars would burn through their fuel faster, and the counts in the clusters would come out wrong. The counts are right. Stellar cooling arguments are among the most powerful constraints in this entire field, and they come from counting dots of light in photographs of star clusters. And here again is the trapping window. If the leak is large enough, the dark photons stop escaping the star and the whole argument evaporates. If it is small enough, they were never made in the first place. So the map now looks like a wall with holes shot through it from every angle. Beams from below, stars from above, walls and cans in the middle. The dark photon survives in the gaps, and in one specific gap, when you set its mass to exactly 0, something genuinely disturbing happens to ordinary matter. Set the dark photon's mass to 0, and the theory does something that looks at first like a disaster. The mixing becomes invisible. Here is why. When both photons are massless, they are interchangeable in a specific mathematical sense. You can rotate the two fields into each other, choosing a new pair of combinations to call your photons, and every observable stays the same. The leak can be shuffled away entirely. For a moment it looks like the whole idea dies. 0 mass, 0 consequence. Then you look at what happened to the matter. You rotated the fields. Fine. But the particles were charged under those fields, and when you rotate the fields you have to rotate the charges too. And the charges do not come out clean. The dark sector particle, which had no electric charge whatsoever, ends up with one. A tiny one. A fraction of an electron's charge set by the size of the leak. Physicists call these milli-charged particles, and the name undersells it, because the fraction can be a millionth, or a billionth, or smaller. Take a breath, because this is one of the strangest predictions in physics. Everything you have ever been taught about electric charge says it comes in units. An electron has exactly one negative unit. A proton has exactly one positive. Nothing in between, ever. Charge is quantized, and that quantization is so exact that we have tested it to 21 decimal places. The universe insists on whole numbers. Millicharged particles break that rule, not by being exotic, but by being a shadow of the rotation we just performed. There could be particles drifting through this room carrying 1/1,000,000th of an electron's charge, and they would feel electric fields and respond to magnets and be part of electromagnetism in the most ordinary way, at an intensity so faint that no detector notices. They would fall through a detector without ionizing it. They would sit in the earth. Some models say they would accumulate, sinking into the planet like a sediment of almost nothing. Searching for them is a nightmare. Every detector we build works by watching particles knock electrons loose from atoms, and the rate at which that happens scales with the square of the charge. A millionth of a charge means a trillionth of the signal. There are experiments trying. One sits above a collision point at the LHC, a stack of plastic bars designed to catch the faintest possible flash from something passing through. Old experiments at Stanford fired beams and looked for particles that barely registered. Nothing so far, and there is a beautiful piece of theory lurking underneath, which is that some deep frameworks predict charge must be quantized in whole units. If a millicharged particle were ever found, it would demolish that prediction and rule out an entire class of theories about how the forces unify. So a fractional charge would be evidence about the deepest structure of physics delivered by a particle almost too faint to exist, which raises a question we have avoided this whole time. If a fifth force is real, why has nobody ever felt it? Forget particles for a moment. Ask the simplest possible question about a fifth force. Would you feel it? If a new force exists with a long reach, it acts like gravity or electricity. It would pull on things. It would pull on you, and on the Earth, and on the objects in this room, and the pull would depend on what those objects are made of, because a fifth force would care about neutrons or protons or something other than mass. That has a consequence you can test with an experiment Galileo would recognize. Drop two objects made of different materials. If only gravity acts, they fall identically, because gravity does not care what a thing is made of. Add a fifth force that couples to composition, and one falls slightly faster. This idea is called the equivalence principle, and it is the foundation Einstein built general relativity on. Break it and gravity itself becomes a different theory. So physicists test it obsessively. The best laboratory version uses a torsion balance. Hang a bar from a fibre so fine that a whisper of a force twists it, put different materials at each end, and watch whether anything pulls one end harder than the other. A team in Seattle has been refining this for decades, and the fibre is so sensitive that they have to account for the pull of the mountains outside, of the water table changing under the building, of a truck parked in the lot. Their answer is that objects of different composition fall the same to within a few parts in 10 trillion. Then a satellite went up and did better. It carried 2 nested cylinders of different metals, falling around the Earth, free of every vibration and every truck. It measured to about 1 part in 1,000 trillion. The same answer. Everything falls together, so a long-range fifth force would have to be feebler than gravity by roughly a factor of 1 trillion. Sit with how absurd that is. Gravity is already pathetic. The entire mass of the Earth pulls a paperclip down, and a magnet the size of your thumbnail rips it off the ground. Electromagnetism beats gravity by roughly a factor of 10 to the 36, and we are saying the fifth force must be 1 trillion times weaker than the weakling, which drives the whole hunt back to the same conclusion from a completely different direction. If the fifth force exists and is anything other than pathetic, it must have a short reach. It must have a massive messenger, so the force switches off before it gets far enough to be noticed. Give the dark photon a mass, and the torsion balance goes quiet because the force never crosses the gap between the 2 ends of the bar. Everything is consistent, and it all hangs on one assumption that a group of theorists decided to attack, that the messenger's mass is a fixed number. Here is an idea so mischievous that it took years for the field to take it seriously. What if the new force's mass depends on where it is? Nothing forbids it. A field's mass comes from how the field interacts, including how it interacts with the matter around it. Build the theory so the field responds to the density of its surroundings, and the mass stops being a constant. It becomes a local property. Now watch what that does. In deep space between the galaxies, the density is almost nothing. A few atoms per cubic yard. The field is light there, its reach is enormous, and the fifth force operates freely across millions of light years. Come into the solar system, the density rises, the field gets heavier, the reach shrinks. Come to Earth, into a laboratory, into a room full of steel and concrete and air, and the field becomes so heavy that its reach collapses to less than the width of a human hair. The force turns itself off precisely where we are standing. Physicists call this a chameleon, and the name is exact. The field changes to match its environment, and the environment we always test in is the one place it is guaranteed to hide. The cruelty of this is exquisite. The torsion balance measures nothing, and the satellite measures nothing, and the reason is that both are made of matter, sitting in matter surrounded by matter. Every experiment we know how to build carries its own blindfold. Worse, the effect protects itself. In a dense object like a lead ball, the field gets so heavy inside that it cannot escape. The entire interior of the ball becomes invisible to the force. Only a paper-thin shell on the surface participates. So your test mass, which you carefully made as heavy as possible to maximize the signal, is mostly inert. Adding mass makes it worse. The counterattack is one of the cleverest experiments in modern physics. If dense objects are shielded, then use something that is not dense. Use a single atom. Teams built atom interferometers, machines that take a cloud of atoms cooled to 1/millionth of a degree above absolute zero, split each atom's quantum wave in 2, send the halves along different paths and recombine them. If anything pulled on one path more than the other, the recombined waves show it as an interference pattern. A single atom is far too small to shield itself. The chameleon cannot hide from it. So they put a heavy metal sphere inside a vacuum chamber, dropped cold atoms past it, and looked for a pull that ordinary gravity does not predict. They found nothing, and they carved away a large chunk of the chameleon's parameter space, which means a fifth force cannot even hide comfortably. The gaps are closing from directions the theories never anticipated. So step back and ask the question this whole hunt is really about. Suppose it is all real. Suppose the leak exists and the twin of light is out there. What is on the other side? If the dark photon exists, then dark matter has a force, and a sector with a force is not a fog. It is a world. Think about what our own force gave us. Electromagnetism took a soup of protons and electrons and built atoms. Atoms built molecules. Molecules built chemistry, which built every rock, every ocean, every cell, and every thought anyone has ever had. All of that came from one massless messenger and a charge. Give the dark sector the same ingredients, and the same machinery starts up. Dark charges attract, dark atoms form, a dark proton and a dark electron settle into orbit, and the orbit is quantized, so there are dark energy levels, and dark spectral lines, and a dark chemistry. Physicists have modelled this seriously, and the constraints are sharp, which is the good news. The strongest comes from a cosmic collision. Two galaxy clusters ran into each other about 100 million years before the light we see left them, and the wreckage is called the Bullet Cluster. The hot gas from both clusters slammed together and stalled, glowing in X-rays. The dark matter sailed straight through, and we can see where it went because it bends the light of galaxies behind it. Dark matter passed through dark matter without noticing, so the dark sector's self-interaction has a ceiling. It cannot be a sticky, colliding, self-slamming fluid because we watched it fail to slam. There is a second limit from the shape of halos. If dark matter could radiate away its energy, the way ordinary gas does, it would cool and collapse and flatten into a disk, exactly as ordinary matter did when it formed our galaxy. Dark matter halos are roughly round, so the bulk of it cannot cool, which leaves a possibility that is genuinely eerie, a fraction, not all of it. Suppose a small percentage of dark matter carries the dark charge and can cool. That fraction would do what ordinary matter did. It would radiate, collapse, and flatten into a thin dark disk lying in the plane of the Milky Way threaded through the stars, a second galaxy, occupying the same space as ours, made of matter that has never once touched us. The sun would be orbiting inside it. The solar system would pass through its plane periodically. Astronomers have gone looking for the gravitational fingerprint of such a disk in the motions of stars above and below the galactic plane, and the data is tight enough now to rule out anything substantial. But not to rule it out entirely, and the whole picture depends on one number, the leak, which we have spent 30 chapters failing to measure, which is where the story stands right now, in the middle of the year, with a verdict finally coming. Because several machines are being built or upgraded at this moment, and within a decade the argument that started in a small Hungarian laboratory will end. The good news about this entire mess is that it is decidable. Every anomaly in this story is a claim about a specific particle at a specific mass with a specific coupling, and that is the kind of claim that dies or lives on evidence. The machines are already under construction. Start with the Hungarian anomaly, because it has a deadline now. The Italian experiment that saw the small excess is upgrading. Better detectors, more positrons, a finer scan across the energy range. They are chasing the same resonance with several times the data, and the excess will either grow into something undeniable or shrink into the noise it may always have been. When they finish, the number will be settled. Two other groups are coming at it from different angles. One in Germany plans to fire electrons at a target and study the pairs that come out with a spectrometer built for precision that nuclear physics has never had. Another is preparing a version of the Hungarian measurement with detectors that share none of the original assumptions. Then there is the beam dump at CERN, which is not finished with us. They have collected close to 1 trillion electrons. The plan calls for 5 trillion, that is roughly 5 times the sensitivity, driving straight through the shaded band where cosmology says the door should be, across a wide range of masses. If the simplest dark matter models are right, that machine either finds something or eliminates them. A more ambitious version is being designed in California. It takes the missing energy idea and adds a crucial upgrade. Instead of only measuring the energy that fails to come out, it tracks the incoming electron so precisely that it can measure the momentum the electron lost, event by event, one particle at a time, at a rate of billions per second. That machine would reach coupling strengths 100 times below anything today. Underneath the LHC, they are planning to widen the drain. The little detector in the service tunnel worked, so the proposal is to dig a cavern down there and fill it with instruments staring back up the beamline, catching everything the collider has been firing into the dirt for 15 years. The wall experiment in Hamburg is upgrading its mirrors and its detector, aiming for a 1,000-fold improvement over where it began. And in Japan, a machine colliding electrons and positrons is accumulating data with a detector that can catch events where a single photon appears and nothing else. Energy in, one photon out, and the rest gone. It is one of the cleanest ways to catch an invisible particle ever devised. Add it up, and the next 10 years close most of the remaining room, which means we are living in the last decade of the question. Somebody watching this in 2040 will know the answer, and it will seem obvious to them, the way every settled thing seems obvious once it settles. There are only two ways this ends. Either a machine finds a bump that survives every check, and physics gains its first new force in a century, or the map fills in completely, every corner shaded, and the answer is that the door was never there. And that second outcome is far stranger than it sounds, because the sky is still telling us that 5/6 of everything is out there. Look at the light around you. It came from somewhere. A bulb, a window, a screen. It crossed the distance to your eyes in a fraction of a nanosecond. And it did the thing photons have been doing for 13.8 billion years, which is carry the news of one piece of matter to another. If the leak is real, every one of those photons is slightly the other thing. That is the claim we have been chasing all night, and I want to leave you holding it properly, because it is easy to lose in the machinery. The proposal is not that a strange particle exists in some distant corner of the universe. It is that the light in this room, right now, is contaminated. That every photon carries a faint whisper of a field belonging to a world that has never touched ours, and that the contamination was baked in during the first instant after the Big Bang, by particles too heavy to ever be made again. The whisper would be the only thing connecting us to 5/6 of everything that exists. 10 years of searching has produced a map with holes shot through it from every direction. A dying star in a nearby galaxy, ruling out one band. Ancient star clusters, ruling out another. A trillion electrons fired into a block of metal in Switzerland. A laser fired at a wall under a park in Hamburg. 2 metal cans in Illinois shouting through a shield. Antennas in silent rooms, listening for a tone from everywhere. A detector in a drain, staring back up the beamline through 300 feet of rock. All of them finding nothing. And in a small building in eastern Hungary, a bump that will not go away, echoed by an excess in Italy at exactly the same mass, sitting at a significance too weak to believe and too specific to dismiss. That is where we are. That is the honest state of the hunt in the middle of 2026. I want to be careful here, because it would be easy to end this on a promise nobody can keep. Nobody has found a fifth force. The muon anomaly, which for 20 years looked like the surest sign of one, dissolved into a calculation. The Hungarian bump may go the same way, and the smart money says it will. That possibility is worth as much as the other one, because here is what the searchers actually accomplished. Physicists took a question that sounds like philosophy, whether there is another world sharing this space, and turned it into a number they can measure. Then they built machines to measure it. Then, when those machines found nothing, they built better ones, and shaded in another strip of the map, and did it again and again for a decade, knowing that the most likely outcome of a career spent this way is a limit rather than a discovery. That is the part that deserves the awe. The dark photon may not exist. The willingness to spend a lifetime finding out anyway is the most human thing our species does. The room is getting smaller, the last corners are being lit, and somewhere in the next 10 years, in a laboratory that probably already exists, a machine is going to run, and the answer will come out. Either the door is there, or we are alone in a universe that is mostly something else, and it has nothing to say to us at all.